Let's get started. We have Jeff from SkyMind. SkyMind is a company behind Deep Learning 4J. Yeah. And I guess, yeah, it's Jeff.
Thanks. Yeah, I just realized we're better known as Deep Learning 4J than SkyMind. So yeah, again, I work at SkyMind. I'm a software engineer at SkyMind. I'm working on the Python interface to our Deep Learning 4J platform, which is written in Java, and so data scientists can actually start, people can actually start using it other than software engineers, because most people in data science use Python, and understandably why, because it's way easier. And I also do, also optimize deep learning algorithms on Spark, and Deep Learning 4J is meant to be distributed, so we have integration with Spark, and that's what I'm working on as well. And I'm also an ex-data instructor at Galvanize, a data bootcamp back in San Francisco. It's a pretty good track record. If you are interested in data science on a more elementary level, you can go check it out, Galvanize in San Francisco. So, image retrieval. I like to usually set out the goals for my talks, like at the beginning, so you know what you get yourself into. So I'm just going to, for the first part of the talk, I'm just going to give a survey of what image retrieval is as kind of a framework, regardless of technique. So image retrieval is kind of, you can use deep learning with it, you can use other traditional machine learning methods with it as well. So I do not want you to think, oh, image retrieval, we must use deep learning. Those are kind of two separate things. And of course, hopefully today I will convince you that deep learning is the way to go for image retrieval. And that, hence the second part of my talk is going to be about image retrieval using autoencoders. And that's an unsupervised method to do image retrieval, or otherwise known as image search. Some of you might hear that as well. And there is also a supervised method for image retrieval using convolutional neural nets. And finally, the third part and last part of my talk, I'm going to go through the existing deep learning ecosystem in terms of software. Cool. So any questions before we start? Cool. So for the overview. So image retrieval really falls under the umbrella of information retrieval. And what it really is finding similar images given a image query. And the same applies to document retrieval. Finding a similar document given a document query. And that's all to it. Like image retrieval is just finding similar image given an image query. And I don't know if you guys, how many people have heard of Google Image? Yeah, so this is like an actualization of image search or image retrieval. You're basically able to upload a photo, either by the link or by the image, and then it would give you results that based on matching other images to the image that you put in. So this is pretty cool. I thought I'll show that, but I would not go into this too much. I would not strip the fun out of doing this yourself. So going into more applications, it's all cool, but what can I use it for? So one of the applications that I've heard of and know people that are already doing in the industry is real estate. So given a person that actually likes this kitchen, I want to recommend people houses with a similar kitchen. So I'll match this image with other kitchen images. And if they're similar, then I'll recommend it to that person. And then another one is perhaps tourist destinations. So let's say I post photos on my Instagram, and they're photos like these, scenery photos of places that I've been to. I want to, based on the photos that is on my Instagram, I want to recommend places for me or for other people to go to. And perhaps the last one, but not the least, and more related to eBay perhaps, it's product matching. So given the person buys this product, I want to recommend them the similar products, so to boost my sales. So I don't know if eBay's doing that, but if they aren't, they maybe in the future. Okay, so here are some applications, and I just want to reiterate, image retrieval is kind of just like a recommender in that sense. If retrieval is kind of an alien word, recommender should be a bit more friendly. It's just recommending images based on a given image. you basically compare your query image to other images and return the top K most similar image. And that's all to it on a very high level. On a more like lower level, like as in practically how it's done. So you have a bunch of images that are in your database, and then you will resize them to the same size, and then you vectorize it. And basically, when I say vectorize, I mean one row now would be an image. And machine learning, you always scale your data as well. And then here is the trick. Dimensionality reduction. You do the dimensionality reduction on the matrix of images. And these are techniques such as PCA, SVD, autoencoder. And you can use more traditional methods like PCA and SVD, but today we're going to focus more on autoencoders. And then after your dimensionality reduction, you have a trained model, and then you will feed all your images through the trained model again, and then you end up with a reduced dimension. So your vectors are going to be shorter, essentially. So if these are 28 by 28 images, and you vectorize it, it's 784 long vectors. After your dimensionality reduction, it will be, let's say, 10 numbers, or however many numbers you want. And these are images in your database, and you do the same thing with your query image. You feed it through the trained model that you have trained all your existing data on, and you get shorter vector as well in a lower dimensional space. And then you do cosine similarity between your query image and all the existing images on a lower dimension. And then you return the ones with the K most highest cosine similarity. Is that clear to everyone as a framework? I mean, this is kind of important before we kind of move on.
Well, one thing you might point out is where the deep learning part is.
What's that?
You might point out where the deep learning part is.
Oh, the deep learning part is in the dimensionality reduction. And yeah, and you don't have to use the deep learning part. And autoencoder is the deep learning technique. I'm sorry if I haven't made that clear. So yeah.
Yes. So on the dimensional reduction, so I have a question. How much to reduce versus how do you decide? Is that something you'll go at a later point when you look at the image? Because that's where you would be taking a lot of the computation.
Yeah, so there are a few considerations here. One depends on how big your database is. So one reason for reducing dimension is that you're doing like cosine similarity here pairwise.
Yeah.
So there's a lot of computation. So you want to, if you have a lot of data, you want to shorten it even more. Obviously, you will lose some data as you shorten it to like 3 numbers, for example.
Right.
That's too low. Like something like 10 to 20. I mean.
But can you, from the reduction, can you see what you lost in the image? Is there a way to visually see what you lost, or this is just going to be numbers that you reduced?
Yeah, there isn't a really direct way you can. With PCA, you can see how much data is retained. But with autoencoders, that's a little bit. I mean, you can see from the reconstruction. So I'll talk about that later. But yeah.
There's one thing going also, which would be kind of cool, the third column that talks about, in essence, about standard document search. And so when the question comes up, is that had you done that? I'd ask, what are some of the similarities and differences in terms of vector length and computation speed for these individual portions of the process?
So you're talking about document.
This is, you could have gone and have, suppose you wanted to go on and do document retrieval,
Oh, okay.
standard Google type stuff.
Yeah.
And it turns out they go on and do cosine similarity. They go on and do a bag of words, put the stuff down there. The difference, though, is also one of the lengths of the vectors that you have inside this. And so that's a question I've got is, how far does that stuff go on? What's the compare, in terms of computational complexity, or in terms of runtime burden, what is the difference between doing standard text search retrieval versus image search retrieval?
It should not be different if you cast it to a lower dimensional space.
It depends on how low the dimension
Yeah,
is, right?
exactly.
Okay, so the bottom line is you can cast it to a low enough dimensional space that they're similar.
Yeah.
Okay.
Yeah.
Can you give
Oh yeah, that I'll go into. So this is kind of like a main mental framework that I want you to have before we move on. All right, last question.
Just one clarification. Here what you're trying to do is find images that and are similar in some way to the original image. Early on when you were talking about the previous page, some of those, not this one, the one, Google, the one, like some of those images are metadata that are related, like if you're looking at a beach, any other image that has a location metadata attached to it might be shown as related, but the images may not in any shape or form be related.
So
Like the picture that you had,
this one.
like the beach and
Yes.
that picture, there is no way that those two will be related, the one on the right
On the right.
and the second
Yes.
row. Yeah.
Oh yeah, sure. Like from a metadata point of view.
From
like,
metadata, you can relate them, but
Yes.
not from image comparison, right? Or am I missing something?
Oh, I mean, this will be similar to this, right?
Will not be similar, right?
They will not be similar, right? Like intuitively speaking, like.
But his matching is not based on image data. His
It
matching
is, no.
is based on the image,
The image itself.
not any metadata associated with it.
So I think you guys kind of got it, like at least a high level. I can answer more questions at the end. So, okay. So why reduce dimensions? Because it yields a more generalized representation of the image, and it's more robust to noisy images. Basically, it performs better, and as I've mentioned, it's faster computations. And why deep learning? Like, deep learning happens here, and why is it? Why don't we just use PCA or SVD, which is some traditional techniques? So PCA and SVD assumes, reduces dimension assuming the original feature space is a linear manifold. And autoencoders assume it's a non-linear manifold. But if that is hard for you kind of to understand what manifold is, I can draw an analogy such that if I give you a bunch of straight lines to reconstruct the original image, are you able to reconstruct it as well as if I give you curved lines? So that's kind of, if you can grasp that kind of high-level analogy, then this is what it's about. And hence, autoencoders yield better representation. All right, so here we go, the deep learning part. So this is what I want to go slow, and this is like the kind of deep learning 101, like the feed-forward net. Like, so you have the input layer, which is your data, and then you have a number of hidden layers, and then you have your output layer, which is basically logistic regression, doing logistic regression. And softmax is basically multiple logistic regression on multiple classes. And so if we ignore the hidden layer, you can represent logistic regression in terms of the neural net. So just connecting the input layer to the output layer, and output layer is basically a logistic regression function. So that we all know. So the magic of neural nets really come from the hidden layers. So what are hidden layers? It's called hidden layers because you don't observe the output. The final output here is like probability of it being a cat or being a dog. So assuming your image, your input is the image. So, and what the hidden layer really does is transform your original feature space. So these are, like in green, these are called activation functions. And basically it's similar like to a Python function. You have an input, and then you do some transformation, and then you have an output. And basically these hidden layers would transform your original feature space into something where the output layer can easily classify. And you can have multiple hidden layers. And deep learning is really a phrase coined for like 3 or more hidden layers. And I know this at this point is probably still a bit abstract as to like hidden layers. What do? They do this magic and they transform your original data to something that's more easily classified. So I find this extremely helpful in understanding. It's an animation, by the way. Extremely helpful in understanding what hidden layers do. So this is like a 2-dimension. Obviously, the input is not going to be in 2D. It's going to be more, but like this is the screen. I can only show 2D. And the red and blue are like classes, like cat or dog. And as you're going through the hidden layers, this is what is happening to the feature space. it is twisting and transforming it, and then you can see at some point you can draw a very clear line between red and blue. And this is what, on a very high level, hidden layers do. And there are different activation functions you can use and try to transform, to kind of twist and turn the feature space in different ways. And I also want to emphasize the fact that there are things called weights connected to these hidden layers. So each of the arrow is a weight. So a weight is basically numbers that determine how much you twist and turn in which direction. So, and that's what training neural net is about. It's optimizing these weights so that you twist and turn the feature space in a manner that could be easily classified at the output layer. Cool. So that is a very short intro. Actually, that's a very short intro to deep learning, and that's kind of like the basis of all neural nets. And so let's move on to scarier stuff. Autoencoders, very big word. But it's really like a feed-forward net. So if you see here is the output layer and input layer, and here's the output layer, and then in between you have a bunch of hidden layers, right? Except the output layer is not like a probability of it being a cat or dog, right? Output layer is just a reconstruction of the original input layer. And basically there are two phases to the hidden layers, and phase one is encode. So that's like how you reduce the dimension. So like, let's say a 28 by 28 image, and then you will reduce the dimension by a bit to 500, and then you reduce by a bit as well, again to 250, and then to 10. They're kind of, like how you decide these numbers are kind of still empirical at this moment. So usually people go 2x, like whatever your first layer is, you just divide it by 2. But obviously the more layers you have, it's harder to train, it's going to take more time, it's harder to tune. So it's a common practice that you start from a shallower, just less layers, and see how the result is, and then tune from then on. So after we get to the reduced dimension of 10, we go to the second phase, where we re-expand the reduced dimension and try to reconstruct the original feature space. So these two layers is basically the mirror of these two layers. And that's how autoencoders are usually set up. So if you have 250 here, you expand it back to 250 and to 500 and to the original feature space. And after that, you have an output layer that is a reconstruction of the input. And then obviously, at the beginning of the training phase, it's not going to like resemble the input very much. And hence the concept of the error between the input and output. So there are different loss functions, but you can think of it as like a general error between the difference between input and output layer. And this error then gets back propagated through the hidden layers. And then that updates the weights and decide how it would be better to kind of reconstruct the feature space next time when we go forward again. So you can see this forward and backward propagation. Backprop is it's a phrase that's very common to neural net training. So, and so that's how a neural net is trained. You kind of go back and forth until maybe a certain iterations is met, or like the error is low enough, then you stop.
Do you have any guidelines based on your work in terms of the number of layers you put in for an autoencoder and the width?
I would start with one. I mean, it depends on how complex your image is. For something like MNIST, which is the hand digit data set, one autoencoder layer, just like the 10 in the middle would do. Like obviously, if you have more varied set of images, that is going to take more layers. But
Is this what you guys use?
this is actually what Jeff Hinton presented. So I think that's the first ones that we used. But yeah, at this point, there are no clear guidelines as to if this, then this kind of thing. And the whole thing with deep learning is we want to make it quicker, so it's quicker to iterate on these things.
The training is supervised?
No, it's unsupervised. So the output output layer is a reconstruction of so the input layer is just basically a bunch of images, right, vectorized.
Right, well, I'm naive, so when does it know to stop?
So
Right.
after a certain number of
Oh,
iterations,
iterations,
or
okay.
if the reconstruction is good enough, then we stop.
Okay.
So if the error is low.
Oh, okay.
So does the reducing and the reconstruction, do they have to be symmetric, the 250, 250?
In general, yes. That for computational reasons, people can like make this not symmetrical, but usually like in textbooks and all that, it's usually symmetrical. It's unlikely that you would make it not symmetrical.
And just to be super clear, so
Yes.
the error rate, you meaning you're looking for features in the output and you're comparing it to the features in the input and you're seeing if they're close. Very
Yeah.
similar.
So the output is we're trying to mimic the input
Right, right.
in the output layer.
And it's not even, unless I'm correct, it's not even features, it's the image. Okay, you got an
Yeah,
image going
yeah,
in, you got
yeah.
the image coming out.
But
Hopefully, it looks
it's-
the same, hopefully it's the same image, and if it turns out bitwise they're the same, you won, hooray. If it turns out, and if they aren't, you sit there and grind until you figure, at least, well, it does look like a cat at least, so then stop.
you couldn't have put it in better words.
So you're comparing every pixel with every other pixel.
Yes.
Okay.
Well, in vectorized form, right?
Okay.
Like, obviously, it's not just the image. Image is 2D. You vectorize it, right?
Okay.
As I've shown like earlier. Cool. And then you scale it as well. But like, essentially, like on a high level is what.
Okay.
What's said. Okay. So this is what I basically said. And for deep autoencoders, there are different tricks that Jeff Hinton has basically invented. And I'm not going to go to those because those are in his paper, and that's kind of the thing that made autoencoders kind of viable for this kind of problem, or like complex image search problems. Basically. So now we've trained the model, like we have to use it, right? So when we use it, we just take the first half. We have the input, and then we encode, and then we get the reduced dimension. So 10 numbers per image. Yes.
Sorry, I guess it's a bit connected to the previous slide. I guess I missed some point. So how do you, you mentioned that the goal is to, the input layer, the output layer somehow mimics the input layer. right?
Yes, exactly.
So what kind of error function are you using? Because it's,
You can use mean square error. That's like,
because it sounds to me that, yeah, I guess probably I'm missing one point that you first go to the end of the pipeline to reconstruct that. And so it's basically the same thing as the input layer, is very similar.
yeah, it should be. I mean, like if it's trained properly.
Okay, so you are somehow testing the reconstruction to see that whether it can.
That's exactly it. So we are able to use the trained autoencoder to get a reduction in dimension. So basically 10 numbers that represent the image may be better than the original image itself, in terms of just retrieving similar images.
Have you guys ever done stuff like, stripping the color, just stripping all the color out entirely, or do you keep, when you do your stuff, do you keep the colors in?
We usually keep the colors. I mean, you can grayscale it and do the same. I mean, grayscale is a form of dimensionality reduction as well.
Right, exactly.
Because it's an image, the color image is a 3D tensor. Like there's RGB, there's 3 channels, but yeah, I'll leave the
But
color
it
in.
happens to be a transformation that still makes things recognizable to humans, especially if they're colorblind. Okay, so it turns out which makes it a little unique. Anyway, you've answered it. Thank you.
Yeah, but yeah, usually we keep the colors and let the autoencoders deal with it. So here I've actually ran a simple autoencoder, and I put in a query image, and then I get the 5 most similar images out. And then you'd be just like, yeah, what's the point of you showing me this? The thing is, I actually written code, and a thing that I usually find that I'm not getting out of meetups is that I don't have code. So I have provided code here, and I'm going to go through it briefly, but again, don't worry about it, it's in a GitHub repo. You can, and based on what I've said, you should be able to follow this very easily. So I read in the MNIST data set, and MNIST is basically just a bunch of handwritten digits. And I scale it, and then I take the first one as the query image. And then here I train the rest on an autoencoder, and I use the sigmoid function. And 10 units, and then learning rate is just to do with how much you update the weights. And iteration 5 is basically how many times you go back and forth. And dropout rate is a regularization term where you just randomly drop half of your neurons. That sounds crazy, but it works. It prevents overfitting. And so you train it. This takes a minute or two. You're running it on your own at home.
Sorry, any reason for using the sigmoid function except for that?
You can use other functions as well, like rectify linear or tanh, but yeah, there's something you can try, but it's not.
Zero and one, right? Go between zero.
Yeah, go
They'll
between.
send all the value between zero.
Oh yeah, actually that's true. Yeah, I've scaled the value between 0 and 1, so it makes sense to use the sigmoid function because it's bounded between 0 and 1. And tanh is -1 and 1. So it depends a little bit on your data as well. So after I've trained the model, I transform my query image, and I transform all my data. And you can see a reduced shape. There are only 10 columns left. And then you get the top K similar images. And here you are. So this is really for you to kind of get your hands on something and get your hands on something and play with it at home.
So I just want to be clear. So this works on sort of naive images, for lack of a better term. So it's got to be like high contrast.
No, this is just something that you can run in 5 minutes.
Okay.
Yeah, I mean, I'm not going to do a very complex example that takes 2 days to train.
No, I understand that. But I mean, but this technique really is.
No, it works on very complex images, and you just have to add like enough hidden layers to take into account that complexity to reconstruct the.
But the image, the object of interest is the image is the object of interest. It's not embedded in just some random images. Like.
No, you can have it like that doesn't have to be the only image, only thing in the
picture.
image.
Oh,
yes.
The only image. Okay.
Yes.
I get
The only, kind of just to repeat what you just said, the only thing special about your code is the data set that you've gone over and fixed here, and then also the levels you've decided to put inside your autoencoder.
Exactly.
Other than that, if people had pictures of their summer vacation and wanted to go on a train at 500, 250, 250, 500,
Yes.
they just have to make those sex substitutions in your GitHub, and they can run it.
Yes, one caveat, it's going to take too long to run it in Python, and I'll talk about that later. But
Okay.
this
Well, I'm like thinking of like, well, I want to find a beach ball in images. And so there might be a bunch of noise that I don't even care about, but I just want to find all the images with beach balls in it. Right? And so,
yeah, so overall the image has to be similar to some extent, right? You can't have
Okay,
you
so
can't have
the-
one
so-
beach ball in one
right.
image and then
Right, right.
5 cats and a small beach ball in another image. Like,
Gotcha. So it's,
so there are techniques to take into account of that. It's called it's basically called patches. You use patches of the image instead of using the whole image.
okay.
So, but
Okay.
I'm not going to go into that.
Okay,
That's
no,
something
I
more advanced.
I understand better. And so, but this is independent of scale and orientation, and so this technique will work.
Oh,
regardless of-
this what I'm presenting now is dependent on orientation.
Okay,
Like it's the
okay.
whole image.
Okay.
So if you use patches, or if you rotate the patches is basically like gridding the image, and if you rotate the patches, then
Okay.
it will become like precision or orientation invariant.
Okay.
So when you've got an output of, let's say, 5 images there, is there a ranking of those images?
Oh yeah, there is ranking from left to right.
Okay,
Yeah.
so the most similar is on the left.
Yeah. Yes.
So how do you improve this model? How do you add more layers instead of adding layers and changing the architecture, change the hyperparameters? How do you decide those choices?
Yeah. So if this is not sufficient, like just having one layer of 10 is not sufficient, one trick you can do is probably blow up the feature space. Let's say you have 784, I can blow up to 2000 and then reduce again. So that's one of the tricks that you can do.
But how do you decide that it's not sufficient?
I mean, you
How do you say that adding the layer would help more instead of doing
I mean, adding layers will help more. The only problem is it's going to take a lot longer to train. That's the problem. It's not like adding layers is not going to do better. So you have to kind of keep in mind that, oh, it takes this amount of time to train to even see the results. And yeah, so the more layers you have, the more complexity you're able to take into account, basically.
So you said that these were ranked, correct? So if I were to change the ranking and said the first and the third were the ones I wanted because of the loop in between, right? The dark thing where the second one does not have. How would I have to change the algorithm so that my ranking would change? Or there's nothing you can do about it?
I don't think in that specific instance with the loop you can do it. Maybe I'm not comprehending the question.
No, but
correctly.
prior when they used to do character recognition, they used to have these counts of loops and things like that, right? Where you don't have the loop over here, right? The two out there, there's a loop, right? There's a dark spot.
Maybe state it a little differently. Let's pretend that, in fact, you'd like to have the algorithm recognize the second and the last one as being not similar at all, because they have no
Yeah.
loops.
Yeah.
Okay? Now, it turns out, if this is supervised training, you
Yeah.
can simply say, these don't match.
Yeah.
Okay, so in the input, when you wound up doing this thing, saying, that one and that one are not twos, okay, these others are twos.
Or you can give it weights, like you can say how much of a 2 is this.
There you go.
So this is unsupervised, so there's only so much you can do with unsupervised. If you have labeled data,
Right.
then you can, which I will cover like afterwards. So yeah, but given like no labels, a lot of just unlabeled data, you're able to do this, which is quite something to say. I mean, not this MNIST data set. So one complaint with neural nets is always, but I don't understand it. Like, what is it doing? So if you visualize the weights, then it kind of gives you a glimpse into how the neural net thinks. If that makes sense. Like, so you can kind of see like there's a 2 here, and there's maybe a 0. But my point here is, in general, neural nets are quite impenetrable in terms of interpretability. So, but like this is kind of like what you can do though, to kind of like get a glimpse of it. So you'll be visualizing weights here, basically, in your encoding part. Cool, so moving on to, yeah.
How are you visualizing?
Basically the weights is a matrix, and you just plot.
You take the matrix over
You scale, you probably have to scale the weights as well, and then you,
the weights of one leg, or you take the weights of one leg and
yeah, the last layer of the encoding.
so you just take them sequentially and what the vector of the weights, right? And then you create them in a matrix.
Oh, it's already in matrix form. I can go into like the very specifics of it.
Then the matrix.
Yeah, I'll explain the shape of it, like when we can dive into the shape later. But yeah, so convolutional neural net, it's different in the sense, it's different from autoencoders in the sense that it's a supervised learning technique, and basically is what I have just shown in the first 101 feed-forward neural net kind of thing. But you can think of a convolutional neural net. Don't worry about the convolution, and just treat the convolution as a hidden layer. And you still have your input, it goes into a convolutional layer, and probably a bunch of hidden layers as well. And then you have your classification as to whether it's a dog or a cat. So that part, I think we all agree there. And in order to use it for image search, you would basically take the numbers just before the part where it outputs a probability of it being a cat or dog through the softmax. So for now, just ignore what convolution is, because that way you're easier to kind of grasp what the supervised part really is. So you don't actually do classification on it. You skip the output layer. Instead, you take the activations just before the output layer. So you take the activation of maybe your last hidden layer or the convolutional layer, and then you use that as your reduced dimension. But you will still train it as if it's as a supervised problem. So you would train it such that you're optimizing for classification of whether it's dog or cat, and you go forward and backward. The training is exactly the same as a supervised neural net. But the way you would use it is that you would drop the output layer and just take the activation of the second last layer. Cool. By the way, this is not an accurate representation of convolutional nets, but just to kind of get across the idea how to use how do you do image search with supervised learning. That's kind of the point I want to get across. But fortunately, we don't have to train these convolutional neural nets. We don't even have to know what they are if you don't want to know, because there's a thing called pre-trained nets, the magic of pre-trained nets. And pre-trained net is basically is usually trained on the ImageNet data. So ImageNet is a competition where there's a bunch of images, and then there's 1,000 labels of various things, like scene, banana, wine, just random things. And then Google or these research teams, they enter this competition and build convolutional neural nets that is able to best predict these labels. And then they save these models. If you're a Python person, it's like pickling, they save it in a binary format, then you can load it in and just use these pre-trained nets. So you can just feed, you don't have to do the training part yourself. So the supervised training part is already done for you. You just kind of have to feed your images through the pre-trained convolutional neural net. And this is the ImageNet data, and this is GoogleNet, as you can see, a real convolutional neural net. There's a lot of layers. This is not something you can run on your laptop, and it's probably clusters and stuff. But yeah, this is the input layer, and that's the output layer. That's the layer before just the output layer. But yeah, so
How many layers?
you can count afterwards.
So that is actually representation.
Yes, you can just Google that. But yeah, but you say, where's the code again? Where can I even start loading the pre-trained net? So in GraphLab, which previously GraphLab, now known as Dado, they provide functions to load these nets, and then if you want to just get started and see some results, then you can probably just Google this. I'm not going to go through it. They have extensive documentation and tutorials on this kind of stuff. All right. So convolution. So how much time do we have? I think we do have enough time. All right. So kind of going back to convolution. Convolution is a way of compressing a signal. In our case, it's an image. So for a convolutional neural net, a convolutional neural net typically would have a convolutional layer and then a bunch of hidden layers. So I'm describing what's happening in the convolutional layer. So the input to convolutional layer is going to be slightly different from just the vectorized form that I talked about. It will be an image, a 2D matrix. So this is the height, this is the width. And what convolution does is basically compress the image in a way that would then obviously downstream help us classify what the image is. And so how do we compress it? So, so we have a thing called a kernel, which is basically a schema for the weights, how we compress the image. So it's a 3x3 matrix in this case. And how you would convolve the kernel with your original image is that if you look at the example on my left, would be placing the center of the kernel onto the pixel that is in question, and then basically do element-wise multiplication, and then sum them all together. So in this case, you can see 42 correspond to the 1, and the rest are 0. And then you add them all up. Obviously, this is going to be 42. So this is effectively like denoising your image. So if your image has a lot of noise, then it's able to kind of average out the noise. But obviously, how do I decide what kernel this is? That's the point of convolutional layer, to kind of learn these as weights. So this is kind of a high level of what a convolutional layer is. There's a lot more to that. I'm not going to go through the whole convolutional thing. I find the CES 231 Stanford course headed by Kathy, which is a PhD student in Stanford, to be kind of like the go-to source for convolutional neural nets. So if you want to get started with convolutional neural nets, I highly recommend this source. So okay, hopefully you have a brief idea as to how to use supervised or unsupervised learning to do image search or image retrieval. So now I'm going to switch gears and go a little bit more into the practical side of things, which is the deep learning ecosystem. So what software is out there for me to perform this kind of stuff? I've shown you like a toy example in Python, and that is something that it's a toy example. Neural nets, it's to some extent an engineering problem because it's very computationally intensive, and hence it's not something that you can run on your laptop, given like the size, a reasonably sized data set. But having said that, I will show you all like the things that the libraries that I found. And Python, there are a lot of Python implementations, and a lot of them are Theano-based, and they all suffer kind of the same kind of problem. You can run it on GPUs, it'll be a bit faster, but yeah, in general, if you run on CPU, it will just never finish. Well, I mean, like for MNIST, yes, as I've shown, but the C libraries, Cafe is kind of the canonical one that a lot of researchers use, and well, Theano is written in Python, but it compiles to C code, so I put it on the C as well. And then there's deep learning 4J, where you're kind of like the oddball player in Java, like that does deep learning with Java. And why do we do it in Java? Because deep learning 4J is conceived to be integrated with production systems that are mainly written in Java. Most backends in most companies, if you do a survey, probably most of them are written in Java. And we have the whole stack of all the neural nets that you will ever encounter at this point. At least the mainstream ones. There might be a few oddball ones that we haven't taken into account. But our nets are quite complete, let's put it that way. And the final thing that I think that makes us really special is that we have our platform is architecture in a way that would be distributed. So I keep mentioning like how hard, why is training neural nets hard? Because it takes long. The cycle is really long. But if you can distribute the tasks of training neural nets, then that would be the ideal scenario. So you would chunk your data up, and then you train the model, and then you do parameter averaging of the weights. And that's the vision that we're working towards, kind of like shorten that cycle from 3 days or a week to like half a day or 2 hours after you lunch, come back, stuff is done. So the sky's really the limit because you can like, if it doesn't run fast enough, you just kind of increase the number of workers. And to do this, we have integration with Spark. And we are working towards integrating all of our neural nets with Spark.
You have your own hardware, or you use like
So we are collaborating with NVIDIA, which will provide our GPU clusters.
So we're using like a Jetson or something
Jensen?
Well, what hardware are you using from NVIDIA?
The GPU cards. So typically, how many of you know of Spark? Okay, so most
Very
people.
popular.
Yeah, most people know Spark. So typically, Spark runs on CPU. Right? If you start a Spark cluster, it's CPU by default. So DL4J basically is kind of a bridge to run things on GPU. So it has operations that will load stuff onto GPU and then like load it back down once it's done. So yeah.
Can you talk about what scheduler you're using? Are you written your own GPU scheduler?
Yeah, that work is mostly done by our founder, Adam Gibson. So he has written basically a NumPy equivalent of, like a Java equivalent of NumPy. He implemented the whole NumPy in Java, and it's supposed to run with GPUs as well. And so the whole software stack is like kind of from the ground up. There is ND4J, which is the NumPy stuff that I talked about. There's Canova, which is basically pandas in Python, but kind of like it builds on top of ND4J, which is NumPy, but allow you to just kind of provide a folder of images, and then it will do all the vectorization and all that pre-processing for you. And then DL4J, which is Deep Learning 4J, really sits on top of these two software stacks. So we have basically three main libraries that we have to support. Well, two libraries to support our third library, DL4J, Deep Learning 4J. So we are still working in sprints, and our stable release is coming very soon though. It's around mid-August or September. You can expect the API to be stable and this stuff to pass the test and to be usable. Right? Like basically usable. Like basically if you don't want to contribute, come back in mid-August or September and you can you can check it out. There will be an optimized version, so the stuff that you've just mentioned. It's kind of like how fast is it, like how do you scale? That stuff will come in October or November, like kind of the release that you can use. Obviously we have stuff in the oven, and the Python interface will come around that period as well as things get more stable, and we can build kind of like an API that exposes DL4J to like a wider audience. And I think that's pretty much it. Yeah, and we are completely open source, so feel free to go onto our website, go to our GitHub, and contribute or participate in Gitter. It's completely like free, as you can see.
Very good.
And today's repo, so slides and the code that I've shown you is. Yeah, so maybe a photo, like if you want to just note down there.
Yeah.
So DL4J, that's a stack that you can, like I can go to Amazon and bring up a GPU instance and configure the stack on it. And then
Not now, but like when we release our when we have our stable release, yes.
Okay.
What's different between your product with another more popular, similar,
Distributed.
yeah, it's called H2O.
Oh, H2O doesn't really they do feed forward nets.
They say, I attend many.
Yeah, they do
They say
distribute.
they can do deep learning.
Yeah, feed forward nets, which doesn't include convolutional neural nets.
Oh,
and
they don't
also
do
include-
convolution.
That's what I know of. Maybe they have changed, but I think I'm pretty up to date on that one.
Yeah, they more focus on machine learning.
Yeah, their forte is their boosted trees. That's why. Yeah. So that's how we're different. Any more questions?
Post this slide online.
Oh yeah, this is the link. My GitHub account is JYT109.
Does it have the slides itself?
Oh yeah, yeah, the slides and the code. Okay. I hope you guys learned something and
Very good.
enjoy.
Very excellent.